Right, so we have looked at the concept of impulse, introduced the idea of momentum, and seen how a force acting on an object over time can change its momentum. But what I want to turn to now is this concept of the conservation of momentum. You know, energy is really important because it's a conserved quantity, which gives us predictability. Well, momentum has the same kind of role. It's very important. And so let's dig into this conservation of momentum. Now, so far, we've been looking at momentum as it relates to a single particle. And so we've been having an object that's been moving. We've been able to calculate its momentum. We've been able to calculate the impulse that acts on that object and determine how much the momentum would change and how fast it would be moving after that force has acted. But everything's been just focused on a single particle. And momentum's important there. But here's the thing. Momentum's greatest power is really revealed when we apply it to collisions between particles, all right? And so that's what we're going to be moving into for the rest of our study of momentum, is trying to understand how the concept of momentum really helps us to analyze collision processes that go on between different objects, okay? Now, what I'm going to do in this video is really lay the theoretical groundwork for that. And so this is very kind of mathy. We're not going to do any problems or plug any numbers into things yet. I just want us to see where the conservation of momentum principle comes from. And so what we're going to do is, turning to collisions, we're going to consider that we have two particles, two objects, object 1 and object 2. And object 1 is moving towards object 2 with an initial velocity that's to the right, and object 2 is going to be moving towards object 1 with its own initial velocity in the left negative direction, okay? Now, these two things don't have to be the same. If they look the same length, that's not intended. They're moving at their own speeds, buzzing along in their own directions, and they're going to eventually collide. Now, when they collide, it's going to be just like, you know, what's going to go on there is what you expect, kind of like the ball hitting the wall and bouncing back. We're going to have two objects that are going to hit each other. They're going to change their shape probably during that collision just a little bit. And what's going to happen is that object 2, as a result of this collision, well, it's going to exert an average force on object 1. And that's what this arrow represents right here. This is the force that object 1 experiences during this collision process. And we're looking at the average again. We know that that force probably isn't going to be the same amount throughout the whole duration, but we can work with the averages and go from there. Well, object 1 isn't the only object that's going to experience a force. Object 2 is also going to experience a force, and it's going to point in this direction. As object 1 hits object 2, object 2 is going to feel a force that's going to the right. And of course, after they hit and they collide, they're going to separate. And then what we expect to happen is that we got our two objects, but maybe now object 1 is moving off to the left and object 2 is moving off to the right. And they don't necessarily have to have the same velocities that they had when they hit. Maybe object 2 is moving a little faster in this direction than it was in this direction at the start. So the magnitudes of the initial and final velocities for those objects aren't necessarily the same. So that's the basic kind of diagram of a collision process. We got two objects colliding, they're exerting forces on each other during that impact, and then after all is said and done, they go off and do their own thing, moving at their own velocities, okay? Well, what I want to do is I want to focus in on this centerpiece when they're actually in contact with each other. Now, they're exerting these forces on each other, right? But we know from Newton's third law that, well, those two forces, they've got to be an action-reaction pair. The average force that's exerted on object 2 is going to be the same as the average force that's exerted on object 1. And so Newton's third law just tells us, hey, the average force created by 2 on object 1 is going to be the negative of the average force on object 1 that's caused, or I'm sorry, on object 2 that's created by object 1, right? And so this is just a statement of Newton's third law of motion. Those forces have to be equal and opposite to each other. And so we're writing vectors here because we're indicating directions with negative signs. Now let's think about how we could write these average forces in terms of momentum. Well, we know that the average force that's exerted on object 1 Well, that can be given to us by the impulse equation, and the same thing here. And so what we get is that the average force that one feels, well, that's got to be equal to its change in momentum divided by the amount of time that that force was acting. That's just the impulse equation solved for the average force. And in the same way, the average force that one exerts on two, well, it's got to be equal to the change in object two's momentum divided by the amount of time that that force acted. Well, it's not really a stretch, I don't think, at this point to see that these delta t's have to be the same. Those momentum changes are going to occur as long as these forces are in play, and they're going to happen for the same amount of time. And so what that means is that I can divide the delta t's out of this equation, and what I'll wind up getting is that the change in the momentum of object 1 has got to be equal to opposite the change in the momentum of object 2. In other words, so there it is, the change in object 1's momentum is equal but opposite to the change in object 2's momentum. Okay, so we're already seeing, this kind of reminds me of kinetic energy and potential energy. You know, they had to be equal in amount but opposite in sign. If we gain potential, we lose an equal amount of kinetic energy. Well, if one object gains 10 Newton seconds of momentum as a result of the collision, then the other object has to lose 10 newtons per second of momentum as a result of the collision. And so that's what this equation is telling us. Now, let's write this out. Let's write the delta p's in terms of what they really are. Delta is just shorthand, remember, for writing changes. And so we know that delta p1 is going to be equal to whatever the final momentum of object 1 was, minus whatever its initial momentum was. And of course, then, by this equation, that's going to have to be equal, and I've carried my negative sign down here. But delta P2 is going to be the final momentum of object 2 minus its initial momentum. Now, let's just do a little math. I'm going to distribute this negative sign through here. And so that's what I've done. So the only difference between this and this is I've pushed the negative sign through. So that means we got a negative final for object 2 and a positive initial for object 2. And then as a final step, what I'm going to do is I'm going to pull all the final terms, anything with a final to the left and anything with an initial to the right. And when I rearrange those, hopefully you can see that what we're going to get is that if I add the final momentum of object 1 with the final momentum of object 2, then that's got to be equal to the initial momentum of object 1 plus the initial momentum of object 2. Okay? So again, that looks a lot like those energy things we did before with potential and kinetic energy. But now let's think about this. What is this term right here? If I add the final momentum of object 1 to the final momentum of object 2, what is this? Well, that's just the total momentum that's in my system of particles here, these two objects, after the collision. So this is the sum of all the momenta of those particles. So that this term, the left, that's the total momentum that's present after the collision. Well, what's this term over here on the right? Well, that's going to be the total momentum before the collision. I'm adding the momentum particle 1 had to the momentum that particle 2 had, and so this is the total momentum before. And so what we get is that the total momentum that's in those objects after the collision, all the momenta added up together, well, that's got to be equal to what all the momenta added together were before the collision. And so what this is saying is that in the absence of any external forces, the total momentum of a system of particles is conserved. I mean, the only way that I could make the final any different than what it started out as is if I had some external force from the outside that suddenly decided to act on one of these particles while they were colliding. That could mess things up, and then the totals wouldn't be the same. But if I don't have any forces coming from the outside, then I have that momentum has to be conserved, okay? Now, what this means, the total amount of momentum may change for individual particles. I'm not saying that the momentum of object 1 is going to be the same after the collision as what it had before the collision, and the same thing for 2. These two velocities right here could be different than these two that they had before. But the thing is, if I add up the momentum, then the total amount of momentum up here has always got to be the same as what it was down here. And so when you have two particles colliding, you get conservation of momentum. And this again gives this a really powerful predictive property, because if we wanted to analyze objects that are going to collide, then we could analyze those processes using the fact that momentum must be conserved, and that we can then use that to maybe predict how fast the objects are going to be moving after the collision, which would be very powerful for us. Now, one last thing I want to point out, like I said, this is all just kind of putting the principle out there. We've done all this for two particles that are interacting, but I want you to notice something, is that while we've derived this for two particles or two objects, it's going to apply to any number of objects that compose a closed system. If you've got 6 objects all moving and they're colliding with each other and doing stuff, as long as there's no external forces, then the total momentum of all 6 particles combined has got to be always the same constant value. And so a real example would be particles, maybe making up an ideal gas that's inside a container. Okay, those ideal gases, we model them treating them almost like they're billiard balls, just bouncing off one another. Well, the total momentum of that system has got to be conserved as long as there's nothing from the outside putting more energy or exerting forces and influences on the system. And so this is the conservation of momentum principle. This is very powerful. And what I want to do now, after this video, is just look at some different ways we utilize this law of conservation of momentum to analyze some collision problems.